we need to have a healthy attitude to respect even these insignificant problems with ESD. Once you are aware that they are occurring and that they can lead to worse problems or to frustrating situations, and you take a step to rectify it before you have hard failures where it's identified as a failure, you're doing a very, very good thing in your life. And I think part of the problem is there's not enough knowledge about what simple, easy steps I can take that really do matter and do work. It's a little bit of a subject that's just secondary enough, just low enough priority that it doesn't quite get, it's not visible to everyone.
Hi, I'm David Cram of Apple Service. I know you'll be thrilled to hear that the computer service industry has a problem that many of us have never really faced before. Sparks. The kind you get on a dry day when you touch a doorknob, only much, much smaller. So small you can't see them, you can't feel them. They never used to bother us much. Integrated circuits were pretty coarse 10 years ago, but now we have circuits so small and so fragile that very low voltages can make chips like these stop working, or worse, cause them to look like they're working but do weird and unreliable things. And it's getting worse. Just about every computer product made today has chips in it that can be damaged by the charge that's just resting in a necktie or a synthetic sweater. We're talking about ESD, electrostatic discharge. Here's what happens. When some dry non-conductors separate, they each take an opposite charge. If there's a conductor nearby, the non-conductor will induce a charge on the conductor, and the conductor discharges it when it gets close to another conductor. And that discharge is what causes the damage. When you walk across a carpet, your shoes separate from the carpet, creating a charge on them. And the charge on your shoes creates a charge on your feet by induction. Now your sweat layer makes you a conductor all over, and the charge clings to the surface of your body until you touch another conductor like a doorknob or another person or an IC chip. Then it discharges in the form of a miniature lightning bolt. If you can feel it, it was at least 3,000 volts. 10 years ago, these things had traces big enough to tolerate a 3,000 volt hit and still work. But some of the traces we're using now are so thin they can be damaged by as little as 30 volts. It'd have to be 100 times stronger for you to even feel it. What do you have to do to generate 30 volts? I'll raise my arm. That's about 225 volts. As you can see, it doesn't take much. There are two kinds of problems. One is the field created by certain non-conductors, such as plastics. The other problem is discharge from one conductor to another. How do we know about all this? I can't touch a working chip and then take it apart and show you the damage. We'd have to use an electron scanning microscope that magnifies several thousand times. It's an expensive process and not something we'd do casually. But if you take the top off the chip and look for damage, and if it looks like this, or this, you know it was caused by a spark. Believe me, if you need proof, we've got tons of hard evidence and thousands of photographs. Actually, we believe in a lot of things we can't see, germs, radio waves, radioactivity, for just a few examples. 150 years ago, the medical profession had never heard of germs, and it took a long time to convince surgeons that they have to scrub up before cutting into someone and not just wash up afterward. Another example is radioactivity. We believe in it not because we can feel it, but because we know its effects can be horrible. Now, it's not so important for you to understand exactly what happens inside the chip when it gets zapped by an electrostatic charge. It is important to accept the fact that something happens, something bad, to the boards that you care about. This is a machine built by 3M to demonstrate the reality of ESD damage. Here we have a MOSFET transistor, but what we're going to see done to it could be done to a CMOS chip just as easily. First, we're going to test one. If it's good, she can set this to 10, and this won't go above 325. So that's good. Now we'll check it for leakage. And as the transistor warms up, that should come down to 0. The tension mounts. Okay, we got a good one. Now I'm just going to charge myself and touch it. And we got a dead short. Let's try it with a new one. Okay, check it for... It's just an overhead transparency foil. I'm not actually going to touch it, but we're representing the kind of problem caused by bringing charged non-conductors close to a chip. Okay. And also this time we're going to put it on a little board. Just put it on there. Okay, now I want to wave this over the top without touching it. I'll wave it under the bottom. Okay, now check it again. Okay, that part's still good. Check it for leaks. Uh-oh, it has a short. And I didn't touch the transistor. That transistor passed a functional test, but it leaks. It's going to fail in the field. And we know all too well when a damaged chip finds its way into a computer, it can have aggravating consequences. How can we stress this? 100 years ago, the medical profession didn't really believe in bacteria. Now they take elaborate precautions to keep their working environment sterile. We're just beginning to realize that we have to be just as meticulous about static if we want our patients, the chips, to survive and function properly. Now, you might be saying to yourself, hey, wait a minute. I've been handling boards for years without protection, and I sure haven't experienced the kind of failures you're talking about. Well, there are two reasons for that. One is that as crowded as these integrated circuits are, there are still a lot of places where a zap won't hurt anything. The other reason is that most of the time, sparks only wound. They don't kill. So if you wound one, and if it fails outright in a month or two, well, you've gotten away with murder. It's question time. Take a look at the following and tell me if the chip on the bench is going to be all right. The cup is a non-conductor, and when he separated it from another non-conductor, it picked up a charge. He placed the charged non-conductor near the chip, and inside the chip are conductors. Let's look at a slow-motion representation of what happens. As the field surrounding the cup envelops the chip, it causes voltage changes in the traces. and if the voltage reaches a level high enough to jump, it burns a hole between the traces. The spark's heat vaporizes the metal, which then condenses on the sides of the hole. If it creates a direct short, we're lucky. Usually it doesn't, and we have a degraded circuit waiting to fail in the field. We can get rid of a charge on a conductor by touching another conductor, but the cup is a non-conductor. How do we get rid of a charge on a cup? The only way a charged non-conductor can get rid of its charge is for the ions, positive or negative, that make up the charge to unite with ions of opposite charge. The air has ions floating free, and gradually the cup will find enough to go back to neutral. But that can take quite a while, hours, days. If you want to hurry the process along, an ionizer generates both positive and negative ions, and as they flow around the object, it takes what it needs. But even an ionizer can't neutralize the charge quickly enough to prevent damage, which happens in the first few millionths of a second. So what can we do? Well, the basic rules are simple. If the device is not being worked on, it should be in a shielded bag. If the device is not in a shielded bag, don't touch it unless you're grounded with a wrist strap or a heel strap. And don't let ordinary plastics or synthetic clothing get close to it. Let me show you something. This is a gadget that spits out positive and negative ions. I'll just prove it to you with my static meter here. Positive and negative. Now zero the meter. This is a new bag. Now I'll put the meter inside, turn it on, zero it, and then I will fire the gun at it, and there isn't a wiggle. Now this bag has a little scuff in it, has a lot of little pinholes, and again I will zero the meter. As you can see, this is allowing 200 or 300 volts to seep through the bag. When we say put it in a shielded bag, we mean a good one, not one with a lot of holes or a lot of scuff marks on it. If you see a worn bag, test it. Don't risk a $100 board to save a 60-cent bag that's already lived a rich, full life. While we're at it, let's see what happens when you put it inside a bag that's anti-static but unshielded. This is a typical anti-static bag, but it's unshielded. I'll put the meter in, zero the meter. Oop, better set that on high. Zero the meter, and as you can see, it's allowing 4,000, 5,000 volts to seep through. This bag won't cause sparks, but it won't protect from a field that's placed near the chip. By the way, we used to think that once the chip was mounted on the board, it was no longer susceptible to ESD damage. Not so. In fact, the possibility of damage actually increases because the traces and leads on the board act as antennae. A proper workstation will have a conductive mat grounded to earth ground, to which the worker attaches a wrist strap cable. When we say ground, we mean real earth ground. The ground wire in a modern building will probably be all right, but you can check it with a ground checker. The wrist straps have to touch the skin, or they don't do any good. If the worker can't wear a wrist strap because it hampers movement, he can wear heel straps, which go from the moist inside of his shoe to ground by passing under the heel. Of course, he must be standing on a floor pad that's both conductive and grounded. By the way, I've had techs tell me that you don't have to worry about grounding unless you have carpeted floors. That's just not true. It doesn't matter what you have on the floors. If you're not grounded, you can't be sure you're ESD safe. The tools used at the bench, like soldering irons, have to be grounded. And devices like solder suckers must be made of conductive plastic. These old blue ones can generate several thousand volts on a dry day. Be careful of heat guns. Some can generate over 10,000 volts directly on your work. And don't use toothbrushes to clean your work. Brushes should be natural bristles, not plastic. And storage bins should be made of conductive plastic. A technician working in the field has to set up a temporary workstation, tie into a building ground, and wear a wrist strap. It isn't enough just to touch the power supply, because every move he makes will generate new charges. And of course, he should never set parts on the carpet or near plastics. Okay, let's see if you can answer some more questions. Watch this scene and see if you can spot anything wrong.
Hi, Dave.
Can I borrow this tool for a second?
Sure, go ahead.
Thanks.
Did you see anything wrong? Let's look again. The tech walks up wearing a synthetic
Hi.
Hi,
jacket,
Dave.
Can I borrow this
probably
tool for a
loaded
second?
with static. He doesn't touch a thing, but when he reaches across to get the tool, his jacket almost touches the work on the bench. And that could be enough to hurt the board. Try this one. Is anything wrong? Take a look. The saleswoman is bristling with static. She opens the box to see if it's the right part, and when she does, she risks zapping it. She should put on a wrist strap before opening it. Incidentally, if the part comes in a box like this, be sure to store it and ship it in the same box. Here's another one. What's the problem? He has anti-static carpet on the bench, and he's just sprayed it. Now, the carpet won't spark to the board he's working on, but it isn't grounded, and the technician isn't grounded either. As soon as he generates enough static, it'll discharge to the nearest conductor, probably the board. I'm sorry to say, all those lovely carpeted benches really have to go. Another problem is that the board was left out in the open. Air is a major generator of static. Think about that the next time you see lightning. And the board should not be bathed in open circulating air any longer than necessary. When you're through working on a board, or when you're through for the day, put the board you're working on in a shielded bag. Try another one. Did you see the problem? She's grounded. All looks good. But what's this? Non-conductive plastic bins? Sitting here, they're probably neutral, but once a bin has been slid out, it can have a charge, and the parts in it could be damaged. Another problem is her hair. Her body is grounded by the wrist strap, but her hair is a non-conductor. Depending on how hard and how recently she brushed it, her hair is easily capable of damaging the piece she's working on. Try this one.
Gina, this is our service
Uh-oh,
area.
here comes the boss with a visitor.
And I'd like to show you some of the equipment that we have. This is one of our logic boards right here. And as you can see, it's very complex with the memory and the microprocessors on it. Get a good feel for it, okay? We'll just place that down there. Let me take you over here and show you over here, okay?
It's easy to see what was wrong, but not so easy to know what to do.
Very complex.
The boss was ungrounded, as was the visitor. Neither had any business touching the board, but what's the technician supposed to do? That's a tough one. He sure can't embarrass the boss in front of a visitor. He could wait until the boss is gone and then trash the board. After all, you have to assume that any board handled like that is at least wounded and in ways you may not be able to discover before it gets back to the customer. Realistically, you can't discard a board that passes functional tests, but at least the board should be retested and burned in again. Now let's take a quick look at some of the things we'll have to do to protect our boards from ESD damage. Technicians will have to adapt to grounded workstations and get used to wearing straps. The salespeople, the clerks, even the boss will have to resist any temptation to touch a board unless they've grounded themselves first. On-site service technicians will have to take the same precautions the mainframe people take, or risk being tossed out by the informed customer. And since some computers have open tops and peripheral cards, even end users will have to be taught proper grounding techniques at the time of sale. Grounding to the chassis isn't as good as grounding to a good earth ground, but it's a lot better than not grounding at all. Just be sure the unit is plugged in and turned off. End users will need to know how to handle sensitive parts. In fact, we want to educate the end user to look for proper grounding procedures when he selects a service center.
Hi, here's the board that I called you about.
Thank you very much.
Thank you.
Because when the customer brings in a card for repair, he should know that if it's not protected, he himself may have damaged it.
We'll do what we can.
We all have to observe 3 simple rules. If you're not working on it, shield it, either in a bag or inside a computer system. If it's not shielded, don't touch it unless you're grounded. And if it's not shielded, don't let non-conductive plastics get close to it. We want the personal computer to be as reliable as the toaster. But if it does come in for repair, we want to be sure it goes home fixed. It's up to you.
You know, even from personal experience, I've had a lot of my own equipment, and I'm not working day in, day out, passing a lot of equipment through my hands. It's what I own and use. I've had a lot of it fail for ESD reasons. I mean, one of the key architecture features of the Apple II that was a huge plus for the whole industry getting kicked off actually came about because of an accidental ESD experience.
Tell us about it.
Sure. The first design of the Apple II said the cheapest memory chips are 1 megahertz. A TV line scans across for 40 microseconds of video and 25 microseconds of blanking. So I gave the video circuits, in the first Apple II design, gave the video circuits 40 microseconds in a row, 40 cycles of RAM. And then I gave the microprocessor 25. And I thought holding the microprocessor off for 40 microseconds was plenty safe. All the specs assured it. The engineers on the phone assured me that it could go for 2 milliseconds. But the Apple IIs I was demonstrating, they would fail. All of a sudden, the processor would go bad. The 6502 would go bad. So I'd plug a new one in, and it would work fine. And I had this dead 6502, but for some reason, it still worked in an Apple I. It was a very weak effect that caused it not to work in my Apple II design, but it did work in the Apple I design. Well, it forced me to figure out that the electrostatic discharge, one time I actually noticed a spark, and right when it went bad, and I knew that that's what led me on to it really was some sort of electrostatic discharge was not destroying the chip, but it was ruining a parameter that wasn't clearly specified in any data sheets. And I finally determined that, okay, you cannot hold this processor off for 40 microseconds. You can when it's brand new, but you cannot a week later. Every single one I used, you could not a week later. And that led me to search for the fact that now the 2 megahertz RAMs were inexpensive, and by going 2 megahertz, we could have video processor, video processor, video processor. It's a very famous characteristic of the Apple II that helped make a lot of its architecture work so well and give it such great performance. And it came about because I was trying to solve an ESD-related problem. ESD protection, when it's a disastrous failure, it's spotted instantly. You know, we can all put a weight on that. One of the worst things about ESD failures is that sometimes they're partial. They are intermittent. They cause a computer that will occasionally run for a few hours and then crash, but it can't be traced. You try to run all the tests on it, everything seems to run fine. These intermittent problems are the worst ones. They're the hardest ones for technicians or normal people to deal with. You can go for several months before usually the problem gets worse, is the only way you ever do get it rectified. If you have a sloppiness about your whole approach, eventually it's going to lead to some of the more disastrous problems, particularly later in your own career.